From our vantage point on Earth, the Sun appears to be the ultimate expression of scale. It contains over 99% of the solar system's total mass, looming over the planets as a blinding wall of plasma. Astronomers, however, categorize our star as a G-type main sequence star. It is a yellow dwarf. This modest classification allows the Sun to process its hydrogen fuel over long periods. It burns with a consistency that provides a stable energy source for roughly 10 billion years. Human perception often inflates the Sun's importance based solely on its proximity. In the context of the wider galaxy, it remains a quiet, middle-of-the-road observer. To find true physical scale, we have to look toward our neighbors. Sirius A possesses twice the solar mass and shines 25 times more brightly than our own star. The escalation continues with red giants. Arcturus swells to 25 times the Sun's radius, while Aldebaran reaches a volume 40 times greater than our solar baseline. At the extreme end, objects like the Pistol star dwarf these examples entirely. It releases more energy in 20 seconds than our Sun does in a year, fueled by a mass nearly 100 times greater. This unimaginable scale suggests a level of cosmic power that seems absolute, but we have to determine if these massive structures are a sign of ultimate stability or the first symptom of impending destruction. Every stage of a star's life and its eventual end is determined by the specific amount of mass it possessed at birth. This relationship is inversely proportional. The more mass a star has, the faster it burns fuel, shortening its lifetime. The largest stars have the shortest lifespans. A tiny red dwarf burns for 1 trillion years, while a giant exhausts its reserve in a few million. Without hydrogen, the star can no longer push back against its own weight. It collapses inward in a violent instant, triggering a catastrophic shockwave. For a star, massive physical scale is a guarantee of a rapid, violent demise. We see this final stage in hypergiants like Betelgeuse. As the core dies, the outer layers swell into a massive, distended envelope that can span hundreds of millions of miles. The sheer volume of these stars creates a bizarre physical disparity. Scuti has a radius 1,700 times larger than our Sun, yet it only possesses about 32 times its mass. Spread across such a vast volume, the average density of the star is hundreds of millions of times lower than our Sun. These are not solid walls of fire. They are incredibly thin, red-hot vacuums. Ultimately, the largest stars in the universe are effectively expanding bubbles, caught in their final dying breaths. While orbiting a stable, small star provides a window for life, but conditions on Earth are also governed by the movements of planetary giants. For years, Jupiter was framed as a protective shield for Earth. Astronomers assumed its massive gravity deflected dangerous comets away from the inner solar system. Modern dynamic simulations have contradicted this reputation, showing that Jupiter's influence works in both directions. Jupiter frequently captures objects from the outer system, altering their paths and slingshotting them inward. This gravity well actually increases the likelihood of impacts for terrestrial planets like Earth. Far from a passive guardian, Jupiter acts as a gravitational sniper, targeting the inner solar system. This constant bombardment was a vital phase in our early history. During the formation of the solar system, the inward hurling of debris was a delivery mechanism. The icy comets redirected by Jupiter carried water and essential volatile materials to a dry Earth. This violent gravitational bullying provided the specific chemical precursors required for life to take root. Our existence was engineered by these misunderstood giants: a modest sun that provided time, fragile hypergiants that seeded the galaxy, and a chaotic planetary sniper that